Okay, now that we've looked at P threads, we're going to do the same for OpenMP. And I'll start with the notes, and I don't want to go through all of the notes. I think some of them are self-explanatory, but I want to cover enough of the key topics that I think you can follow the rest of the details yourself and ask questions. And this is not going to be the only thing we do using OpenMP. So I think the idea is to get you started, not to explain every nuance of the language. And then once you get started and try other things, I'll show you other features and techniques, and you can expand your abilities. So let me start by sharing the screen. Okay, hopefully you see the OpenMP lecture, portion of the lecture. So what is OpenMP? I talked a little about it. It's a extension to a language, which is one thing that makes it nice. Oftentimes when you want to do parallel programming, the first thing people ask for is not to learn a totally new language. So one idea is to extend an existing language. In this case, languages like C and Fortran and C++ are extended by adding certain parallelization constructs as pragmas to the language. So the idea is for the parallelization, as much as possible, to be orthogonal to the functionality. So if you didn't have any OpenMP directives, or if the compiler does not recognize them because you don't have an OpenMP compliant compiler, then the code still just remains functional in the serial sense. Right now, occasionally it's not quite that simple, but oftentimes you could achieve something close to that. It's based, like pthreads, on shared memory multi-threaded programming. You do not express data locality like I was talking about with the NUMA system. You do not say this processing unit should sit near this data because it operates on it preferentially. Instead, you simply talk about which tasks can be done in parallel on different cores, and you think of everything as just a big shared pool of memory that every core can read and write to. In that sense, it's similar to pthreads, except you don't have to program at such a low level. So it removes from you the burden of having to do the detailed, spawning of threads, and joining of threads, and explicitly creating mutexes and so forth. So it includes several sorts of constructs for parallel programming. There are critical sections and atomic accesses that allow you to do transactional portions of code. You can specify the visibility of different variables that you create as shared or private. Creates the idea of a barrier where all threads have to wait until the last one has arrived to that point before they continue. So it has all the basic functionality, it just presents it at a higher level. And it's an industry standard that has support from, I think, 70 something different companies, including Intel and Microsoft and IBM and so forth. Okay, so it's part of the GNU compiler, part of the Clang compiler. You can just specify the -F OpenMP or -OpenMP flag. I guess it's -OpenMP for the Intel compiler. And it will, if you use the header, include the header file, and then use the OpenMP clauses and library of functions, they will automatically be compiled into the code. Okay, so how do we look at an OpenMP code? Well, we think of it as the serial code as a starting point. So imagine we have just a regular serial, we think of as a master thread, and the serial code that's just moving along. And then at some point in your code, this would represent a region that you've decided to OpenMPize, right? So you create a parallel region descriptively in OpenMP. You say, okay, at this point, I'd like to do this block of code or execute this function in parallel using this many threads. And OpenMP takes care of the infrastructure of creating all the threads, but it does it for that block that you've said that you'd like to spawn threads for. And then when that block ends, the threads are joined and the main thread continues. And then you might use fewer threads later to do some other block of code. The idea being that you kind of start with your serial code, you look for the most time-consuming functions, the sort of 80-20 rule, where a lot, 80% of the performance and 20% of the code, that's just made up. But I think it is a way of saying that oftentimes you have concentrated regions in your code of, high performance requirements, or a lot of work in small regions of code, however you want to say it. And and so you use the serial code as starting point, and the parallelization becomes the exception, and you do it in these targeted areas. And I say that because a lot of other types of parallel programming aren't that way at all. You really start parallel from the beginning. You either program in a completely parallel language, or if you do message passing, you sort of do the opposite, which is things that are serial become the exception, and you start from the bottom up with everything being distributed memory parallel. Okay, so I point to these as being like the parallel regions. I have a picture of Amdahl here. You might have heard of Amdahl's law. Amdahl is skeptical of this because he says, well, great, except this is upper bound by the fraction of work which is parallelizable. Because if you have a code which is 90% parallelizable and 10% inherently serial, the most you could speed it up ever, even with a billion cores, is just a factor of 10. Because if the code, say, took 100 seconds to run, and you were able to take the 90% parallel part and make it run in no time at all, it still takes 10 seconds. And so you're kind of upper bounded by the serial portion. And Amdahl's law is a way of saying you, the law of diminishing returns. It's actually more general than parallel programming. But while it's obvious in a sense, it also is surprising the first time you think about it. Because it basically says, if you want to make 100, 200, 1,000, 10,000 core machine, what's the point? Unless you've got true, codes that are 99.99999% parallel. That's unusual because usually you have certain inherently serial components, whether it's, doing like I did a final summation of the partial sums, or whether it's just some I/O or some interaction with the user. Okay, so that was always a confounding aspect of parallelism. Turns out that his observation was a little pessimistic. A guy named Gustafson came along and kind of clarified one aspect of it, which is really why distributed memory parallel programming has been so successful up to now, exascale level computational resources. And that's just because when you get more computing resources, you don't do the same problem faster. You often do a harder problem at the same speed, or something in between, a somewhat harder problem, somewhat faster. Anyhow, that's for another day to talk about that. I just wanted to introduce that topic. So the OpenMP memory model is the same as with threads, and that threads communicate by accessing shared variables. The sharing is defined syntactically, so that any variable that is seen by two or more threads is shared, and any variable that's seen by only one thread is private. And we have defaults for these things, and we have a way of controlling them with clauses. And you don't get around race conditions. You still have to synchronize to prevent one thread from getting ahead of another, or to prevent shared writes from conflicting. Okay, and so it's still hard. It just appears to be a lot easier, and the difficulty is more in thinking than it is in writing code and debugging code, which is kind of what I like about it. Okay, so in a practical sense, what does OpenMP look like? Well, most of the constructs in OpenMP are pragmas. So we're going to decorate our regular C code with things in different places that look like pound pragma OMP, construct, clause. And we'll just use a few pragmas in this first assignment that we're doing. Okay, and that pragma applies to a structural block, which is an entry and exit point, which is a block of C code with braces. Okay, and there are different kinds of constructs, and we'll look at different ones, but the most obvious one is just to express the parallelism. Like I'd like to do a parallel loop, I'd like to do the section in parallel, but there are also things which say this variable is shared among threads, this variable is private, this variable is private, and it is initialized with the serial value upon entering this block, so forth. Synchronization are things like atomic or critical sections, which are very similar to one another. Atomic is really just for like one instruction or one line of code, and critical is for a whole block of code. And barriers, which I talked about before. And there are a bunch of functions, which you can call in the library. Those functions look like OMP underscore something. And they could be simple things, just like set the number of threads, get the number of threads, or they can be more complicated. There might be 30 or 40 functions. Okay, but obviously you have to if-def the functions if you want your code to be portable when there's no OpenMP compiler, but these pragmas will just be ignored by the compiler otherwise. There's no OpenMP compiler. Okay, so let's take a look at a simple example that doesn't do much. Imagine we have this simple loop here. So it sums from 0 to 1,000 all the elements of the array D, like in the example that I gave. Okay. Well, if I put this in a parallel section, so pound pragma OMP parallel really corresponds to sort of you hit this point right here. Okay, so you want to spawn a parallel section. So when I spawn the parallel section, any variables that are defined inside the parallel section are now thread private. Okay, that's just a scoping rule for OpenMP. So that's good. Each thread has its own version of I, each thread has its own version of sum. But what is this going to do? Well, nothing particularly useful. Each thread is going to sum from 0 to 1,000 into D. Now, D is global because it's defined outside and it's not explicitly stated to be private. You would have to change its scope to private here. So things declared outside are by default shared and things declared inside are private. So it's going to sum up the values of this array into n threads, different local variables called sum, and it's all going to print the same thing. Okay, and OMP thread num gives the thread ID, which is 0 to n threads minus 1. All right, so you compile it with the OpenMP flag. It executes the same code several times. Not that interesting. Okay, remember D is shared between threads. I and sum are private. So you should try that out, but you should see that it does not parallelize the loop. It just, well, parallelize in the sense that everyone just does the full loop, doesn't break up the index space. Okay, well, what if we wanted to really do it the way you would imagine? Let's imagine we want to add two vectors. Let's say a vector B, a vector C, and you want to add an element by element to get vector A. So the sequential code looks like this. Okay, you could in OpenMP do, I want to enter a parallel region. You could say, give me my thread number. You could say, give me the total number of threads, and you could do the index start, the index end, just like we did with P threads. Not quite as much work, but the same basic calculation. Then you could say, okay, I want to go from my start to my end and add my piece of the index space. This is a really simple example because everyone is writing to their own memory buffer, right? You're not sharing memory between threads, so it's always an easy example. But you don't have to do that. That's such a common pattern that's programmed into OpenMP at a higher level. And this is sort of what we really need for the homework. So if you want to do that, you could say, okay, enter parallel section, and you could annotate a loop. So this OMP 4 construct applies just to a loop that is directly after it. You can't put this anywhere. This directly applies to a loop, and the loop has to be a for loop that has to have a static bound. And if you do that, you don't have to do a static schedule, although that makes more sense. Then this becomes the equivalent of this without the messy error-prone logic in it. Okay, so this simply parallelizes a loop. So it's very, very simple. Okay, notice that the integer is defined in here, so it's already local. N is presumably defined on the outside, so it's global, that's fine. A, B, and C are presumably declared on the outside, they're global, that's fine. So this works beautifully, okay? So that parallel 4, which is gonna be the bread and butter of your assignment for the n-body problem, has certain requirements for the type of loops it works for, and all of those will be met in the n-body problem. And oftentimes, or typically when you do real OpenMP programming, these two are next to each other with nothing else. So sometimes you could have this, then you could have this, and then other stuff before you close the parallel block. But if it's literally just these two together, they created a joint construct for it, which looks like pound pragma OMP parallel 4. Okay, and this is it applied to the dot product example, which I haven't mentioned yet, but I just wanted to show you that you can specify pound pragma OMP parallel 4 right before loop. Okay, so well, let's look at this. This is a dot product. So dot product is you're summing the pairwise products of two vectors A and B. So A1 times B1 plus A2 times B2 plus A3 times B3 and so forth. All right, if we want to do that, now we've learned we can just have one pragma OMP parallel 4, and we specify that sum is shared, even though by default it would be shared actually among the threads because it's declared on the outside. So oftentimes I turn off, and I'll show you how to do that with the example. I turn off all the defaults, and then I just specify them explicitly for the visibility of each variable. You would say private I, shared N, shared A and B, shared sum. Okay. You put them on the same clause, shared sum, A, B, so forth. But I think it's better when you first start to be explicit. If the attribute that you give to it is the default attribute, that's fine also. But if you turn it off, it enforces discipline until you get used to it. Anyhow, there's obviously a problem here because we run into the same issue of when all the threads are doing this, they could be corrupting the single element of memory that they're writing to. So you can't get away with doing that. So one option you have is to add this OMP critical section. The OMP critical section for each element of the loop will ensure that no two threads write to the same value. But that's really, really wasteful. And it's too slow to be a practical value because you're doing it for each loop iteration. Okay, so I'm sorry, I changed fonts here. It's kind of ugly. But if I show you an improved way of doing this, it would be now I'm showing you the full interface and I'm explicit about each variable's visibility. Again, first private means that the single serial copy of LSUM is 0 here, and it's about to have many copies because I'm making it private in the loop, and I want them all initialized to the same value as the initial value of LSUM in the serial code. Okay, I is private, N and G sum are shared, and so I have to fix something I messed up with this font. But so I pound pragma OMP4, and I do the local sum. Okay, so now I do this whole loop on each thread. Local sum's going to be different for each thread that does it. And then when I'm done, I can do a critical section. And this now mimics what I've done with P threads, right? I do a small number of these instead of a huge number. And so this is an improved way to do it. This is good enough. But it turns out this pattern is so common that OpenMP lets you do it at a higher level. And the higher level way of doing it is to do an OMP parallel 4, but to use a reduction. Okay, so you say OMP parallel 4 reduction. The reduction is a plus operation, and it is the sum variable that is the reduction variable. And so then it just looks like a regular loop, so you don't have to do anything except state how this behaves, and that guarantees that sum will be handled under the hood in this way, okay? Because it's such a common paradigm, a reduction. Okay, so I think that's enough for me to go over because there are a lot of different clauses and a number of little subtleties. But you saw enough there, certainly, to do the assignment. And the way I'm thinking about this isn't, you don't dump all of OpenMP on someone's lap and say, now you've learned it. You give a little bit, and then you do an assignment. And then you do another assignment, you learn a little bit more. And after a few, you start to get pretty good at it. Okay, so this is just sort of your first interaction. We'll do other things that are going to require us to parallelize them to get good performance, and you will get more opportunities. But I think at this point I'll stop. I encourage you to keep looking at the notes and to ask questions, but in the next segment I will move to an example, in particular the array sum example, and show how easy it is in OpenMP.